Hey, my name is Min, and I would like to use this demo to show how you can encode a negative value that is potentially longer than 8 bits using the same idea that was used to encode a positive number. So let's try, like before, same idea. If your number is can be represented with less than 8 bits, then you don't need a rotational amount. Like let's say we have -2. This is the immediate encoding for, this is the two complements representation of -2. As you can see, the most significant part, which we will define as the longest trail of zeros, can be fitted into the bottom 8 bits. So really, to encode -2, all you would need to do is call MVN on this number right here, without any rotational amount, because remember, MVN moves whatever number you gave it into the and into some sort of register with a specified rotational amount, and inverts the number. So if you don't give it a rotational amount, it will just invert this number, and this number inverted is this number. So let's try a number that is longer than 8 bits. So -265 is this entire number right here. As you can see, the most significant parts of this number is longer than 8 bits. By significant, we mean the longest consecutive trail of zeros, which spans from here to here. We don't care what happens in between. We just care about the longest string that starts with a 0 and ends with a 0. So the operative question is whether or not we can fit this string right here into the bottom 8 bits. And if you count it, it's 2, 4, 6. It's less than 8 bits, so it's very probable that we can't fit it. So you can use these arrow keys to try to move it in, and only one move will indeed move it into the correct bottom 8 bits. See, now here's where things get a little bit tricky. So like before, with the positive numbers, we know that we have to rotate these bottom 8 bits back to their original position to get the original number, because obviously the original number is sort of offset from the bottom 8 bits. But here's where it gets tricky. If we were to say that our bottom 8 bits is 1011 1101, which is this number right here, if we rotated it back to its original position, it wouldn't work, because in essence, if you tell ARM that this is your 8-bit number, then it will in reality it will extend the number to be to fill the 32 bits, and the extension, you extend it with a trail of 0. So this is 8 bits, so really we would have sort of 24 zeros in front. So it doesn't matter how you rotate this, you won't match these trail this all the ones that are in a negative number. So a separate idea is, let's say I have this number right here. What if I rotated it and then inverted the entire number? So if you invert this entire number, you would, all the zeros here would become ones, but this string right here would also get inverted. 10 0 0 0 1 0, which is not going to be correct, because if you look here, the 8 bits that should be in there is pretty much this string. I can highlight it. It should be 10111101, whereas it's not this. So in order to sort of circumvent this, what we need to do is pre-invert this string right here, so that when we do invert it, we will invert it back to the correct string. So in essence, what we want to do is start with so this is the 8 bits that we captured right here. We invert it to get 0 1 0 0 0 0 1 0, and then we rotate this entire string back to some sort of the original position, and we can figure it out later there. But let's say we were able to rotate it back to let's say that let's say that we rotated the bottom 8 bits in somewhere within our 32 bits, and if we inverted the whole thing one last time, then we would get 1 0 1 1 0 1 with a bunch of ones, and that is exactly what we want. So we would get a bunch of ones, and somewhere we would get these significant bits 0 1 1 1 0 1, and then the rest is just ones. So that is the main idea. It's a little bit more tricky than the positive numbers, but it's not bad once you get the hang of it. So let's do what we just did with the notepad using this tool. So we've captured the most significant parts of our number, and then before we figure out a rotational amount, we need to say that we want to work with the inverted version of this guy, because starting with the inverted version of this guy, we rotate it back to its some sort of original position, and then we invert it one more time. So let's show the original value. This is what we're trying to match. This right here is the inverted version of the bottom 8 bits, and we can use the arrow keys to move this, but remember, once we move it to some sort of position, we invert it back to get this string right here, and in essence this is what we want to match to the original 32 bits. So let's rotate it. So as you rotate this top number, this number also gets rotated, because remember, this number right here is just the inverted version of this number. So if we keep rotating, we want to match this number with this number. So let's keep rotating. Looks like we are almost there. Okay, so that required a rotational amount of 30 to match. So really the final answer is, because the MVN instruction requires a register, so I just use R0 for example purposes. But really what we want to do is move this number right here, which was the inverted version of the original 8 bits we captured, 30 times, and then MVN is gonna invert it one more time. So I think that was still kind of confusing. So in order to really solidify the concept, I think we need to sort of see this in action. So let's say we started with these bottom 8 bits, 0 1 0 0 0 0 1 0, which is right here. So if we play the animation, so that these 8 bits are going to get rotated, so it's moving through the number, and it's going to be rotated 30 times, and then at the end MVN is going to invert the whole bit string. So in essence, this number right here rotated 30 times gives you 264, but if you rotated the entire bit string representation of 264, you get negative 265, which is the original number we wanted. So that is the idea of encoding a negative number. You need to figure out what the most significant, whether or not the most significant parts of the number can be captured using 8 bits, and then you need to figure out how much to rotate it back, and you need to also do some inversions, because you know, when you have negative numbers, you're dealing primarily with ones. So that concludes the demo for encoding negative numbers.